All right, time's up. I guess we should start. So on behalf of the Hong Kong Academy of Engineering Sciences, welcome to this second seminar of the series, jointly organized by HKAES and the Engineering Faculty of Hong Kong U. So without further ado, I would like to pass the microphone to our moderator, Professor Kenneth Wong, today. Thank you.
Thank you. Oh, okay. Well, thank you, sir. Ladies and gentlemen, so today we are great pleasure to have it's a multi-head, like I said, at the same time, Professor K.M. Look, it's also our alumni, actually, it's from Triple E, Electronic Engineering. So, well, I'm sure that K.M. already gave me a very a concise list, so I try to keep it very brief. I don't want to take up too much of the time from the audience. So he's a fellow of the Royal Academy of Engineering and also the fellow of the Hong Kong's Academy of Engineering. Yes, I'm sure that's there. Also fellow of IEEE, Hong Kong IE, CIE, IET, and Electronics Academy as well. He also received that 2001 Culture Award, 2011 State Technology Innovation Invention Award, and 2017 IEEE APS John Cowles Tenure Award. 2019 that's Hawley, that's Science and Technology Prize, and more recently that's 2022 the Guanghua Engineering Prize. That I know that he's going to take the flight to receive it tomorrow. Is that right? Okay, so I think that's without further ado, let's welcome Professor K.M. Look for sharing with us today. Let's welcome Professor Look.
Thank you. Thank you, Professor Wong, for the kind introduction. And I always feel exciting when I come back to my alma mater, and particularly those good memories refresh in my memory again. And also have so many friends and coming here, and my student is also here. So nice. And I got my PhD, not only PhD, actually the bachelor degree and a PhD here. In that time it's double E department, now it's triple E. Right? And when we were a graduate student, we were working in the Hacking Wong building, but now we moved to another building. Right? And very exciting to come here. When I was a PhD student, I'm not working in antennas. I'm working on microwave measurement. But it's related because microwave measurement needs the electromagnetic theory. So when I joined, in that time, City Polytechnic, become a lecturer, I shift my interest slightly to antenna design, although it still require the knowledge of electromagnetic theory. Right? And fortunately, my change is a good decision, I would say, because in that time, the so-called microwave measurement, you don't have good future. But with the blooming of the wireless communication, so it gave me the opportunity to design different kinds of antennas to fit the development of the so-called 3G, 4G, 5G, and 6G. So today I will share with you some of my work in developing small antenna or low-profile antenna that is particularly useful in wireless communication. In addition to communication, actually, we try to diversify our applications to other areas recently, not only in communications. I don't want to be controlled by those giant companies like Huawei, because everybody working on antenna will serve them. But I don't want my work only serve a giant company. So I try to diversify my interests, but still remain to try to see whether antenna can be useful in other areas. For example, in sensing area and also in medical area. So today I will share with you those interesting things in applying antennas to different areas. And I know we are not all of us are specialists in the electromagnetic theory. So I try not to include any equation in the presentation. Just share with you more pictures and share with you the idea to develop the antennas. So the topic with the title we call the Magneto-electric dipole is a name I give it to a kind of antenna I developed about 18 years ago. And initially, this antenna is mainly for 4G, 5G, but somehow we found that it is suitable for other applications. So these two pictures are the most important antennas that developed by my group in the past, and then it applied quite widely in different applications. Over the past 40 years, the antenna community concentrate our effort to develop low-profile antenna or printed antenna. In the past, about over 100 years ago, we developed this so-called dish antenna, parabolic dish antenna, Yagi antenna. Most of these antennas are quite bulky in size and mainly suitable for communications. But about 40 years ago, in the antenna community, we want to develop very thin antenna that can be mounted on any kind of structure without affecting its original shape to make it more, so we call the aesthetical beauty, and also we look without affecting other performance. The special name for this kind of printed antenna, we call this microstrip antenna or microstrip patch antenna. As you can see, the structure here actually is very simple, right? It's very simple. Just a dielectric substrate supporting a metal patch, and then on the other side we have a ground plane. So basically we have two metal layer. In between is a dielectric material. So the dielectric material is mainly for supporting the patch. The radiation is mainly from the patch. And we try to make it very thin. So the principle is just like a resonator. It's a resonator. The wave actually is traveling between these two metal patch. The metal patch and the ground plane. The wave is traveling back and forth, and they form a resonance structure, just like the musical instrument is a leaky resonator. So the dimension actually control the resonance frequency. And in many applications, we select the major dimension close to half wavelength. So make it a resonance structure. So we can make this kind of antenna using the standard low-cost printed circuit technique, PCB technique at low cost. And depends on the PCB we use. At low frequency, we just use the conventional low-cost dielectric substrate. We can make it at a very low price. At microwave, we may need to use other materials because like the FR4, the loss is low at low frequency, but when we operate the antenna at microwave, the dielectric loss may be significant. So we need to find other kinds of material to support the patch. And other material, in that case, the polymer, we can also use the ceramic as a dielectric substrate. So the loss of this dielectric substrate control the performance of the microstrip antenna. In its original shape, due to the thickness of it, so it's a high Q resonator, high Q. High Q means narrow bandwidth. So over the past 40 years, researchers trying to find new way to improve the bandwidth. In the original design, it's just about a few percent of bandwidth. And the radiation is mainly radiating to the upper side. You're assuming this antenna is mounted on the ground plane. The shape of the patch can be either rectangular shape, triangular shape, or circular shape. We found that the performance is similar. So even for nowadays, such as this very complicated antenna I will describe later, it is still based on the microstrip antenna technology. Right? For this one, I will spend some time on this one in the coming view graphs. So for antenna, we need to connect our excitation to the antenna to feed. We call the feed. The feed can be a coaxial cable, like this one. It's a coaxial cable. Right? The cable is mounted below the ground plane. The center conductor passing through the ground plane, and then connect the center conductor to the upper patch, so the energy can be propagated inside the coaxial cable to the region between the patch and the ground plane. Another method we call the microstrip line feed. So this is a kind of printed transmission line. The wave is also traveling along the region between the line and the ground plane. The wave traveling along this way and then excite the cavity. So the wave actually bouncing back and forth inside the patch. It forms a resonance structure. So in performance, it's very simple. This length controls the resonance frequency. We have other kinds of excitation. I don't spend too much time on that. So just give some idea what is the principle of operation of an antenna. It's just a simple resonator. If you want to describe this by electronic circuit, it's just like a parallel resonator. So if we check the performance of this antenna, usually when we check the performance of our antenna, we plot the real part and imaginary part of the input impedance. We call it input impedance of the antenna. You can see from this real part, you can see that it is narrow, quite narrow. So this curve just shows us the antenna is narrow in bandwidth. Usually, we also measure the antenna by our network analyzer. Network analyzer, they show the reflection coefficient, and it has this form. So from this reflection coefficient, usually we require the reflection coefficient below -14 in real application. So it's also quite narrow in bandwidth. So from the network analyzer, we can check the original antenna is narrow in bandwidth. So over the years, we try to find some ways or methods to improve the bandwidth of antennas. The idea is always simple. We add some parasitic patch. Parasitic means the patch is not connected physically to the original patch. It's just coupled. The energy is coupled electromagnetically to the original patch. So this additional patch can form another resonant point. And this resonant point, if you select appropriately next to the original one, so the two resonants will add together, then you have double resonance. That means the bandwidth is enhanced. Another approach, we get a patch on top of the original one. Still, we don't need to connect them together because this is electromagnetic radiator. So the energy can couple from one patch to another patch. So if we select the dimension of the upper patch appropriately, we can also add another resonance close to the original one. So you have double resonance, bandwidth also increase. The third method is we increase the thickness slightly. Although originally we want it to be very thin, but in some cases it is allowable. For example, we increase the thickness to 10% of wavelength is still okay. So when we increase the thickness of the antenna, the qualitative antenna, the Q factor will reduce. Qualitative Q factor reduced, that means the bandwidth can also increase. So this is another way to improve the bandwidth of the antenna. But when we reduce the Q factor, the thickness increase, then this feed has problem. We found that the feed has some inductive effect. We call it probe inductance. So researchers try to find some way to cancel out this additional probe inductance. They found that etching a U-shaped slot. This slot can introduce some capacitance, which can cancel out the probe inductance. So electronically, we can use the capacitive inductive concept to explain the behavior. As a modification of this U-shaped slot patch we developed many years ago, we found that another feeding method can also provide wideband performance. But like this one, we modify the direct coaxial feed to an L-shaped feed. That means the feed is not connected directly to the patch. Just we add another portion. This portion, together with this one, looks like an L-shaped structure. The energy can couple through this feed to the patch inside. And why we have this structure? Because, it's okay. This additional one, together with the patch, they form a transmission line, actually, using the electromagnetic wave concept. because if this length is close to quarter wave length, the wave can actually propagate along this direction. So this line, together with the patch, form a transmission line. If the length is shorter than quarter wave length in electric circuit, which is equivalent to a capacitor. So this capacitor capacitance can cancel out this additional probe inductance. Why this is a probe inductance? Because the current flowing along this way and then going back, so looks like a loop. So if it has this inductive effect. So we found that we don't need to connect the probe directly to the patch. Just use a L-shaped feed. We can also couple the energy to the patch. This is good because the probe inductance can be cancelled by the capacitor of this line. Then the principle is similar to the U-shaped patch. We can form a good resonator with no Q factor, but without the probe inductance. Additional advantage for the L-shaped feed is that we can add another feed in the orthogonal direction. That means we can have dual polarized antenna. Dual polarized antenna means we have two antennas integrating together. One feed excite one polarization, the other feed excite the orthogonal polarization. This is commonly used in the wireless communication nowadays because in wireless communication, the wave bouncing back and forth in a compressed environment. In one location, you may have one polarization receiving stronger signal. And then when you move to another location, the other polarization can receive better signal. So the system actually checking which polarization can receive better from time to time. So dual polarized antenna is an important antenna nowadays. So we try to develop wideband dual polarized antenna. And this L-shaped feed is particularly useful in this kind of application. In the old day, we can do this dual polarization antenna in the base station only. In the mobile phone, it's difficult. Mobile phone is too small to install dual polarized antenna. But in the base station, we can use dual polarization antenna. This is the 3G base station antenna array. It's a real product fabricated by our spin-off company in China 20 years ago in Qingdao. We have a spin-off company in Qingdao to build this 3G base station. And we can sell some to those giant China Telecom and those kind of company. And so the company initially was quite successful. So after many years, this L-shaped feed technique, our patent already expired. So everybody can use it. So recently we can find a antenna giant company in China. They use this L-shaped feed to build their 5G MIMO base station antenna. It's a huge array of patch antenna excited by the L-shaped feed. And of course, the technique is different from the old day. In the old day, we used the metal plates to make it, but now they use a plastic, the whole structure, and then they coat the metal on it. So it can be built at a very low cost. And we get nothing because the patent already expired. And but we're happy because they use our technology. When we developed this patch antenna for base station antenna, we found that the antenna, although wideband, but it still has some disadvantage. For example, the front to back ratio is not that high. That means the antenna radiation in the front side, but the back side still have some strong radiation. So we try to find some way how to reduce the back radiation. A straightforward way, of course, is you add a large ground plane to block the radiation from to the back side. But in practice, it's not practical, right? You use the base station, you use a large ground plane, it is not a practical way to do it. So we try to find some way to reduce the backside radiation. And then we found that a concept so-called the complementary antenna concept can help us to solve this problem. Now here, I just show schematically. We have for example, you have a vertical electric dipole. So the field is radiating like a figure H shape, right? The wave is like this, going very strong to the two sides. and the field is going down in the same direction. Then you can consider another magnetic dipole. Magnetic dipole is a horizontal dipole. Then the electric field from the magnetic dipole will circulating around. So if you can excite one electric dipole together with one magnetic dipole, then the field can be add together on one direction, but cancel out in the other direction. So conceptually, it's very simple. Right? So if you can find some way to realize the electric dipole together with a magnetic dipole together, then you can form this directional pattern. This is the side wheel. From top view, the E field, the magnetic field is like this, and this is the magnetic dipole. So they also form a cardiac shape pattern. So the whole antenna can radiate very strongly to the front side, but you have no radiation in the minus 180 degree. The outside is the same. So how can we realize this concept? There are many ways, actually. But for our antenna people, we try to find some way. But optical people also, they have their way to realize. Another term is called the Huygens source concept. Since I'm working on microstrip antenna, I try to use this concept to build a complementary antenna. How can I integrate a microstrip antenna with other antenna to form this directional pattern? So this is structure I proposed about 16 years ago, 18 years ago actually, 18 years ago. So this one is, we have two vertical plates, and this portion looks like the microstrip antenna. Previously, I said the microstrip antenna is mounted horizontally. But when you consider, when we rotate the antenna 90 degrees, so it's oriented like this, then the wave actually can traveling between these two plates. So the wave is traveling back and forth. And we have a short circuit here, so the wave can be reflected back. So this U-shaped structure operates like the microstrip antenna. The wave is just traveling up and down. And then at the opening, the wave can radiating out. And we can demonstrate that, we can prove that this is equivalent to a magnetic current. So this aperture is equivalent to a magnetic current. And then we add, on top of it, we add this additional electric dipole. Electric dipole just has two arms. It's commonly, very common use in different applications. But usually it's in the cylindrical shape. But when you change the cylindrical shape with a plate, rectangular plate, the bandwidth can be enhanced. So this portion is equivalent to an electric dipole. And this opening is equivalent to a magnetic dipole. And we excite both electric dipole and magnetic dipole with a feed, just like the L-shaped feed I use in the microstrip antenna. And here we have the transmission line to guide the energy to this portion. So this portion is responsible to excite the electric dipole and the magnetic dipole. Mathematically, this opening, because in this aperture, the field is mainly the electric field. So electric field means it is equivalent to magnetic current. And the current, the electron flowing along this direction is the electric current. So when they add together, if we can excite them in appropriate magnitude, they combine together, we form a very nice radiation, directional radiation pattern. We can demonstrate using the conventional way to show the performance of our antenna. We plot the gain against frequency and the reflection coefficient against frequency. You can see they are too deep. So this point represents the resonance of the electric dipole, and this point is equal to the resonance of the magnetic dipole. You can see we try to offset the resonance slightly from between the electric and magnetic dipoles, so we can improve the bandwidth further. If we try to design both electric dipole and magnetic dipole at the same resonance frequency, the bandwidth will be narrower. The compensation is already very good. No need to be overlapping each other. You can see the backside radiation is already less than minus 20. No need to be minus infinity because for engineer application, we don't need to be very ideal. So just offset them, we have wider bandwidth, and also the backside radiation already improved. Using the conventional antenna, the backside radiation is only minus 15 or minus 10 dB at some frequency. But here we can maintain the backside radiation less than minus 20 dB already very good. And for the microstrip antenna, usually the bandwidth is about 30%, but here we can achieve over 50%. Also, the gain is very stable. So such a simple structure operating at microwave frequency, around a few gigahertz of microwave frequency, in this design, we can have a very good directional pattern. And again, as I mentioned, we need to have dual polarized antenna. So we modify this linearly polarized antenna with a dual polarized antenna. So we chop these 2 pages into 4 pieces and then excite them with 2 feet. So this is another modified version. We call the dual polarized ME dipole. The previous design is suitable for low frequency microwave frequency, but at higher frequency, for example, at the 60 gigahertz, we build this ME dipole with pure metal. It will be very expensive. So we try to use the printed circuit technique to make it. Printed circuit technique. Printed circuit technique is easier because we can realize the vertical wall by vertical vias. We found that replacing the vertical wall by vertical vias still can perform quite well. So this is the first antenna we try to make the ME dipole operating at 60 gigahertz using printed circuit technique. This is another version, a little bit more complicated. We have this via to realize the vertical wall, vertical side wall, and this is the feed. The feed is coupled to the patch electromagnetically. It does not touch the metal. Just to form a capacitance to cancel out the probe inductance. So the structure, the structure is quite similar to the previous one, but this one has an additional advantage to form a dual polarized antenna because we can add another feed in this direction. If you use multi-layer dielectric, then the orthogonal feed can be added to the original one, then we can form a dual polarized antenna. We also found that the bandwidth can be maintained to over 50%. At low frequency is more than 50%. At such high frequency using printed circuit technique, we can still make it with very good performance. This is operating at 60 gigahertz. This design also used by other researchers. For example, we found that they try to use this ME dipole. This is the National Lab in Beijing for remote sensing, satellite remote sensing. They built this prototype for satellite communication. So this one will be mounted in the satellite for remote sensing in the future. I'm looking forward if they have this real testing result in the future. But we're happy that people also found that our ME dipole design is useful for real applications. For array design, we need to find a feed network to combine the energy together. And so the feed network you cannot see here because it is sandwiched below the patch. But if you expand the structure, you can see this is a feeding network. We combine the energy together one by one. The feed network layer is below the patch layer. And this is a radiation pattern because the gain is high, so that you can see the radiation pattern with a very sharp pin, We also found that the ME dipole was applied for the radar application. For radar application, they want to have wide scan beam. For radar, wide scan beam. But to realize wide scan beam, the antenna itself should be compact in size and also has wide beam width. So this is the way they increase the bandwidth. The beamwidth means the radiation direction cover wider angle. They found that they add some parasitic element to the original. This is parasitic element to the original one, the parabolic element is shorter than the ground. The beam width can be increased. Originally, the beam width is like this, but when they add a parasitic structure next to the electric dipole, the beam width can be increased like this. So with this, they can form a very wide beam width scanning for antenna array application. And I think this is by one of my former postdoc, who is a full professor of this Air Force Institute in China. So probably this one is for defense application. And we also found that recently IBM also used this structure to build a millimeter wave module for the 5G mobile phone, and using the mu dipole structure. And because the major advantage of the mu dipole is wide bandwidth and also high efficiency, so they also apply this technique for the 5G mobile phone design. We also continue to develop our antenna, but I may just slightly. For the dual polarized antenna, you need to have 2 layers of feed, orthogonal. But here we try to simplify our structure into 1 layer. But in that case, we need to have the feed. In this gap, we have this feed. In the other gap, we have another feed. So this one, we can have a single layer to build the antenna. And then the feed network can be mounted below the ground plane. For this design, we can see the pattern is quite symmetrical. The gain also quite good. Bandwidth is over this one is 30%. Maybe I can, for array design, it looks like more complicated, right? 2 by 2 element. But for printed circuit, it's not that expensive. We just for printed circuit, I need to excite this 2 by 2 element. And then we can form an array. You can see if we can form narrow beam. The beam can be formed narrow. And also for the particularly useful for this mu dipole is the beam width can maintain very stable with this design. So I just skip this. I don't go into the detail for interesting. To realize high gain array, antenna array, one problem is the side lobe. You can see, although we can form a narrow beam, sometimes there's many side lobes. In most design, the side lobe is not that low. So for the mu dipole is useful for us to realize low side lobe wideband performance. Here you can see this is an array, but those with the dark color means the phase is changed by 180 degrees. To excite the patch with 180 degrees phase, then the side lobe can be reduced from the usual design is minus 13 dB, which can reduce it to minus 18 dB. Just simply change the excitation direction. For example, we excite the dipole in this direction or in that direction, the phase is changed by 180 degrees. And since the mu dipole can be very symmetrical, we can excite it with 0 degree or 180 degree very easily. So this is also demonstrate the mu dipole is suitable for very wideband and low side lobe applications. At microwave frequency, millimeter wave frequency, we can use the printed circuit technique to make it. But at terahertz frequency, the printed circuit technique is difficult. It's difficult to realize. So I try to collaborate with my colleague, who is a nanotechnology expert. So she can use this microfabrication technique to help us to build our metallic antenna. But actually, it's not pure metallic. We use this silicon, and then we call a SU8 polymer. We do etching and then coating. So through this process, we can have an antenna structure at the outer. Looking at the outer surface, it's just like a gold plate structure. And since the surface roughness can be made within a few nanometers, so the material loss can be insignificant. So with this technique, we can build a metallic terahertz MU dipole. We don't need to have the whole structure as metal because at such high frequency, the electromagnetic wave cannot go inside. Due to the skin depth, we call the skin depth, the effect. At high frequency, the wave cannot go inside the metal. So we don't need to build the whole thing with metal. Just very thin of metal on the surface is good enough to work it, to make it as a metallic antenna. So through this process, we can make an antenna. The outer surface are just slightly metal. And of course, we scale down the structure to terahertz frequency to just around 0.1 millimeter. And so we exaggerate this enlarged structure. We have the waveguide to fit this 2x2 antenna element. So with this microfabrication process, we can make a terahertz antenna. We also demonstrate the performance is similar to those MU dipole operating at microwave and terahertz frequencies. Performance is similar, even at such high frequency. We further try to enhance our antenna with the so-called the Fabry-Perot resonator antenna concept. We have the MU dipole as a feed. We form a resonant structure, spherical mirror with a partially reflective surface. So the wave is bouncing back and forth between the partially reflective surface and the spherical mirror. So they form a beam, a Gaussian beam radiating outside. If you have only the MU dipole, the gain is quite low, 6 dB, 7 dBi. But with this additional structure, form a Gaussian beam, the gain can be enhanced to more than 20 dBi. Of course, at such high frequency, terahertz, the surface finishing must be very good and also close to the spherical structure. So my colleague, Professor Pan, can also help me to, based on the microfabrication technique, the dry etching technique, and to make the MU dipole coated with the silicon, and then to do the etching for the MU dipole. And of a spherical mirror, she used this SU8 polymer and use a metal bead to press it to form a spherical mirror, and then do the coating. So basically, she can use this microfabrication technique to help us to build this very tiny but very accurate spherical cavity. So you can see the gain can be over 20 dBi gain with this MU dipole excitation over a wideband from 1.02 to 1.1 terahertz with this MU dipole. If we just use the conventional waveguide, the gain can be 5 dB below, and we can at such high frequency, we can still maintain good return loss over this frequency. Maybe I can skip this one. Sorry. There is another hot area in the antenna array design. We call it transmit array and reflect array. For transmit array, we try to use a planar structure to replace the concave mirror. And for a reflect array, we try to use a planar structure to replace this parabolic structure. The way that we can do is we can add some phase shifting element on this plane. If you can control the phase shifting value at different locations, this planar structure can operate as a convex mirror. Also, if we can change the phase, reflection phase, then this can simulate a parabolic reflector antenna. Since the ME dipole is wideband, so we use the ME dipole as the receiving element and transmitting element. Then we can form a planar structure with this high gain performance. And also, we can make it beam steerable if we can add some phase shifting element on this element. So this explains why recently many people in the antenna community we try to develop different kind of transmit array and reflect array. So with this basic concept, here is the element we developed for the ME dipole for the reconfigurable reflect array. We found a structure like this. With a ground plane, the ME dipole is a dual polarized. And the patch is supporting from the vertical via. So we found that when the diagonal corner is connected, like this or the other, the reflection phase is different, can be changed to different value. So how can we connect this arm or connect the other arm at different location? The way we did is we add some diodes in these 4 arms, right? And we apply bias at the center. The bias line is from below the ground plane. We have a center wire passing through the center. So the diode depends on the polarization of the voltage. If it's positive, this 2 dipole can be forward biased, and this one will be reverse biased, so it's not connected. If you change the voltage from positive voltage to negative voltage, this arm can be positive bias and negative bias. So by changing the voltage, positive or negative, we can connect this arm or the other arm. Then we can change the reflection phase. So the limitation of this design is whether we can have a good diode. Currently, at low frequency, we can buy this diode very easily, but at very high frequency, we can't buy it at the moment. So the reason why I'm exploring the possible collaboration with Professor Nga, whether your group can help me to make this kind of diode in the future, so we can apply it for the terahertz applications. So you can see when we control the bias, change the phase, we can actually not only concentrate the beam, we can also scan the beam electronically. So it depends on which location we change the bias direction over a wide beam width. First one is a 1-bit design. If you want to have a 2-bit design, make it to change the phase only 0 to 180 degrees, we can change it to 90 degrees, then we have a more complicated structure. We have 8 diodes here to connect them together. So this is also not that easy to realize, particularly at high frequency. So we are still thinking about how we can realize this at very high frequency. So I can skip this one. But we can scan it over a wide range with this one. So this is another one for the previous one is a reflect array. But how about transmit array? Transmit array, we have one receiving element below the ground plane. This is a transmitting element above the ground plane. Receiving element is ME dipole. Transmitting element also ME dipole. We can rotate the feed to different direction. To one this direction or the other side direction, we can change the phase from 0 degree to 180 degree. Particular advantage of this ME dipole, you can see the phase change can maintain the same over a wide frequency range. You rotate this 1 degree, the phase change. And then the loss is very low compared over the wide frequency range. And the low cost coupling. Let's skip this one. So this is the prototype we make, and we can see the transmit array can also perform it with narrow beam and some low side load performance. For linearly polarized design, previously circularly polarized design. For linearly polarized design, we need to modify the feeding structure. And we have a dial to control the feed, the energy direction. If we connect this one or that one, the phase is changed by 180 degrees. If we add another arm to here, we add another dial here, so we can select either connect to this part or that part, then the phase also change. So with this 5 dial connection, we can change the phase over from 0 degree, 9 degree, 180 degrees. So we call this 2-bit design. Of course, more complicated. We need to have 5 dials to control the path of the current, to excite the patch antenna. So again, we need to have low-cost dial to realize this transmit array design. This one is more complicated. We have the transmit array with a feed, multiple reflection, reduce the thickness. So maybe I'll skip this one in view of the time. So all I have talked up to now is talking about the communication side. And recently we tried to use it for the medical application. For medical application, one interesting application is for the stroke detection at low cost. Currently, people has the problem of bleeding in the head. The patient needs to be sent to the hospital to do the MRI scan or CT scan. It takes much time. But if we can use microwave at low cost, that equipment can be installed in the ambulance. So at least the patient may be checked initially whether he has this bleeding problem. So actually, this is developed by some group already. They try to use different antennas to realize this system. And in my group, I just try to see whether the ME dipole whether the ME dipole is also good for this kind of application. But for the ME dipole, the reason is that ME dipole has more directional pattern. So when we mount the antenna on the human head, you can see the energy can penetrate inside. This is 0.6 gigahertz. 1 gigahertz, 2 gigahertz, 2 gigahertz, and one vertical plane and horizontal plane. So up to 2 gigahertz, the energy can still go inside. But if you increase the frequency to 5 gigahertz, then the wave cannot go inside. So for this kind of application, the low frequency microwave is useful because the wave can penetrate inside. And we try to develop a compact ME dipole for this kind of application. For this kind of application, we need to match the antenna to the human head. Antenna for the communication, the antenna is facing the space, easy to design. But when the antenna is facing the human head, the loss is substantial and also mismatched. So we need to have some tricks to make the antenna match to the human head. So here we try to add some matching liquid inside the ME dipole, and so it can be. We found that it can also be matched to the human head. With the reduction in size, we can mount H antenna on a normal human head, so we can do the imaging. For example, if this is the phantom we use to test our performance, for this kind of application, it's easier for us to buy a phantom to do the measurement. I don't need to have some collaboration with the medical professor initially because phantom is easy to buy. Of course, once we find our system, our design is good, I will explore the possibility to work with those medical professors. But here we can see, we can detect, actually it's based on the radar technology, we can detect the size as small as 5 millimeter with some bleeding. So this is the first design we successfully developed using the ME dipole. The size can be much smaller than the normal one because it's facing the human head. Human head is mainly water. The water is like electric constant is quite high, close to 81. So the antenna itself can be very small. But even if it's very small, the bandwidth is very wide. Over 100% bandwidth is amazing. So it's good for radar application. This is our second design. And we modified the structure compared with the previous one. This one, we don't need to have matching circuit. And then we can still also identify the location which is speeding location. And with this arrangement, we try to check the polarization, which one is better, horizontal or vertical. And in this design, we found the vertical polarization is still quite accurate. Next, we try to develop antenna for glass, antenna on glass. But put the wheelless antenna on glass is not that easy because of the vertical via. The ME dipole is vertical via. So we try to see whether if we remove this vertical portion, the red line, whether it can still work as a ME dipole. And fortunately, my student, he is also here, Derek, and he found a modification of structure, and then he also adds some so-called metal surface. It can realize as a ME dipole. You can see the radiation pattern is quite directional, and also wide bandwidth. So with this modification via 3 ME dipole, we have the confidence to realize this for antenna on glass. And this just to check whether the performance is good. It forms a narrow beam structure and low side lobe. So it's very encouraging. Just forget about the other detail. So with this initial design, we are trying to build antenna on glass. Why we need to have antenna on glass? Because in the future, we may need to install antenna in many locations, particularly for the 6G, the cell size is very small. If you just put the antenna on the wall, you don't have enough space. But if you put an antenna on glass without affecting its transparency, then it may have many applications. So we try to see how can we realize the antenna on glass. And initially we use ITO to make it, but recently we found that using a fine metal mesh, we can still make a very good transparent antenna with good performance. This is our initial work. We will study more in the future. But anyway, we see that the transparent antenna using ME dipole is also has a future for this kind of development. The antenna on glass not only for communication. We can use it for energy harvesting. So recently, we also work on an antenna for energy harvesting. This is one design by my student. He's also here. And the idea is like this. We want to collect the energy from different directions. And we have a lens called the lumbar lens. Lumbar lens, the idea of lumbar lens, here you can see different color, represent different dielectric constant. So when the wave coming from different directions, it will concentrate to a point. For example, one direction, the energy will concentrate in this point. But in another direction, it will concentrate to another point. So conceptually, we can put antenna array on the other side. Then the energy can be concentrated to one antenna. You then do the rectification to transform it to DC power. But in that case, it's difficult to build array on a curved structure. Difficult. Instead, if we can modify this circle structure to a hemispherical structure, or this modern slightly larger hemispherical structure, then we can easily put the array on this side. So this is the dielectric constant distribution to realize this function compared with this one. Looks more complicated. And the mathematics he uses is so-called the transformation optics. Although this is microwave frequency, the transformation optics also is an approximation, but still good enough for our application. So you can see the distribution looks more complicated, but nowadays it's not that difficult to make it because we can use the 3D printing technique. We just control consider it is subdivided into many small pieces, and then you remove some of the material, you can control the effective dielectric constant. So this is the one we make, and we have the MU dipole as the element to collect the energy, and you can see the different direction, the receiving power is quite similar. This one can also be used for communication actually, but here we just use it for the energy harvesting. We believe in the future, in the 60s, the whole environment has many millimeter wave, which is a loss. And so why not just have some device to collect the energy? Although the energy may not be very high, but may be good enough to drive those IoT devices, many IoT devices in the future. So this may be the last one. Recently, we tried to use the robotic concept to control the shape of the antenna structure. So we have a rod antenna. Basically, this is a liquid wave antenna. Liquid wave antenna, the wave traveling inside the cable, and then the energy leaking out, and usually the separation can control the direction. But if the shape of this antenna can be bent to different shape, then the pattern can be controlled. So here we try two cases. There's a horizontal line, so the energy is radiating upward and downward, horizontally and vertically, so vertical omnidirectional. But when we use this robot to control, the radiation will be changed. It can go downward this way. But if you control other directions, the beamwidth can be controlled. So this is one way. If we can we can change the speed of change very fast. You can change the pattern instantaneously. So this is one what we are doing recently. So maybe I skip this one. So finally, I just want to summarize. Over the years, we have published some books and also some special issues to summarize our performance and design in the antenna. And this is the reason why last year published in the engineering, the flagship journal of the Chinese Academy of Engineering. We summarize our antenna design over the years. And so the working on antenna design give me some prizes. And I'm glad to have this opportunity to get these different kinds of work from IEEE, Royal Academy of Engineering, and also from China. And also recently we have a documentary talking about antenna in our field. So the achievement is not myself, of course. It's mainly due to my students. They own all the credits. I just give them some ideas, and then they realize it. And sometimes I don't give them ideas, they have new results. So the achievement, all this achievement should go to my students over the years, back to 30 years ago, and some of them are here today. So with this, thank you for your attention and your patience in listening to me for 1 hour. Sorry about that, I'm running over time. Thank you.